So thank you very much for joining my talk. I hope you find it interesting. My name is Yoav. I'm the VP of Engineering for Imperva Incapsula. Let me start by telling you what Incapsula is. Well, we're not upgrading our laptops fast enough for Docker to catch up with Docker. Cool. So if you're running a service online on the internet, it could be a web application or a website, you're probably using one of these components, probably all of them. You have your CDN to speed up access to your site. You probably have a load balancer to spread traffic across your servers. You may also be using more security type of services, a DDoS mitigation service, a web application firewall to stop application layer attacks, and maybe a bot manager to control the bot activity in your site, what they can do and what they can't do. So Incapsula is what you get when you take all these components, bring them together into a single platform that is delivered as a service from the cloud. So lots of stuff. We always place ourselves between the website visitors and your servers and protecting and accelerating everything in between. In high level, Incapsula is spread across a few dozen POPs, about 35 today. And we have thousands of servers. Most of them run two types of software. First type of software, we call it the proxy. This is our HTTP reverse proxy. And we use that to implement the CDN, the web application firewall, the bot manager, and the load balancer. And we have behemoth servers. These are really cool. We use them to mitigate network DDoS attacks, your SYN floods, DNS amplification attacks, all that cool stuff. In addition to that, we have the management console where our customers log in. They can make changes, configure their assets on the service, view reports, all that stuff. So Incapsula is a closed network in the sense that you can't just start sending traffic at it. We have to know a few things in order to be able to protect your service. So we, at the very least, need to know your domain name and an IP address that we need to send good traffic to, so where your servers are located. And we have to distribute this information across all our network because we don't know in advance which one of our POPs, or maybe more, will get traffic for your service. So it could be a localized service in a certain area, so we may have traffic, we may see traffic in one or two of our POPs, but it could be a global brand and you have traffic from all around the world, and it could be any one of our POPs getting your traffic. And with a very large number of services protected and new services boarding all the time, and customers logging in and doing changes, the customer configuration database, so to speak, keeps on changing all the time. So we have to make sure that we synchronize all these changes across our network. Lastly, our customers really appreciate the fact that we allow them to be agile in managing their online assets. And whenever a customer does a change on the management console, they can see that change live in up to 60 seconds. And this is something really good, but also challenging for us to keep a large network spread across dozens of data centers synchronized. So the service that we use to synchronize customer configuration across our network is called RevLite. And I won't go into tons of details about RevLite. I could spend a complete talk about that, and it's a really cool, I would call it a small object database. But in high level, RevLite is comprised of three big components. We have the leader repository where all the configuration is stored, and every change that the customer does on the management console is sent to the leader repository, and it's recorded there. The leader repository is hosted, deployed on a single centralized server in our network. And on every one of our thousands of servers, we have a service that we call RevClient. And Revline's job is to synchronize the leader repository into an identical copy of it on the file system of each one of our servers, and we call that repository the local repository. Finally, our application, and that could be the proxy application, it could be the Behemoth application, and other types of applications that we run, they know how to read the configuration from the file system, and we have a protocol so that they can do it safely and online, get all the changes that occur in the configuration. So now that we understand roughly how we manage configuration at Incapsula, let's look at how everything crashed and burned. So on March 10th last year, 2016, one of our customers wanted to apply a custom web application firewall policy to one of their sites. So they went to the management console. They put the policy there. I'll show you. They used a feature called IncapRules, which I can show you in a second. And using Revlite, the configuration change was published across our network. Problem was that this specific rule had a double quotes character in a place that our parser didn't expect to find. And for some reason, it passed validation. So syntax was OK. But when we loaded the rule into our proxy server, it crashed. Not one, but all of them, because we know how to synchronize configuration changes across our network very well. So this is doomsday for us. And you have to understand that when our service is down, all the services of our customers are down. This is an always-on service. So huge brands that you know and use all the time were down. Millions of websites were down at this point. So we're all reliability experts here. So let me ask you a question. What's worse than having your entire service crash? Losing data, that's bad, right? But okay, a problem to get it up again. Great. So true. One thing that is worse than a crash is a crash loop. And this is what happened to us. Why did it happen to us? Because we had the bad, so to speak, rule already persisted in the local repository in each one of our thousands of servers. So our proxy application crashed, started up again, saw this cool new rule with a double quotes in a funky place, loaded it up again, and crashed again. And that went on in a loop. So what is this feature that caused this whole thing to happen? So we call this feature IncapRules. IncapRules is great. It allows customers to apply whatever logic they want into our web application firewall. For example, this is a rule that I created to stop spam in a blog site. You can see that in the rule editor section, you have the rule itself, and our proxy evaluates this rule against the HTTP request that it's now processing. If it matches, if it evaluates to true, then it performs the action. In this case, I wanted to display a CAPTCHA challenge for this bot. So IncapRules, you can appreciate the tons of functionality that it provides our customers. Recently, we built some more functionality into that to do all kinds of other stuff that you would usually do on your load balancer. But it's an inherently risky feature because its configuration, what is required in order to get it to work, is very complex. There's an infinite number of rules customers can write, and there's an infinite number of traffic patterns that can come in and be evaluated with the rule. So the system as a whole is super complex. So realizing that when we built the feature, we built a safety mechanism into IncapRules. And the job of this safety mechanism was to actually prevent a case where our system is in a crash loop. This safety mechanism works by keeping a list of site IDs. Every site is a service registered on our service, and it has an ID, a numeric ID. So in the memory of each one of our proxies, we have a list of the site IDs that the proxy is now evaluating or processing HTTP requests for. And we add to this list the site ID whenever we start doing work for that site. For example, if we start reading rules for this site or evaluating rules against an HTTP request, we add the site ID into the list. And once we finish and everything's okay, we remove the ID from the list. So what happens if we crash? We have a crash handler in our application, and it serializes the list of sites into a file that later on we can, when we start up again, we can read and repopulate that list and know on which sites our proxy worked on just during the crash. So it allows our application to make an intelligent decision on how to gracefully degrade the service according to whatever logic that we want to build. And of course, it's a bit more complicated than that. We count the number of crashes we had for each site ID, et cetera, and we build all kind of logic into that. But in essence, what we want to achieve is to avoid this crash loop in a graceful degradation kind of manner. So obviously it didn't work. Because we were down for 20 minutes, 30 minutes, 40 minutes, I don't remember exactly. But it did require our engineers to go into the system, understand what was going on, look at core dumps, and very quickly, in a few minutes, they found out what was going on. They went into the management console, they reverted the configuration change, and once it was removed from the local repository, system started up again, and incident was over, basically. So that was a tough day for everyone at the company, and I'm sure you all have similar stories, things going wrong in production. I can probably bet that you don't have a more glorious story than this one. But if running a service in production that is mission critical to your customers was easy, we wouldn't be having this conference, right? So we went on to do a post-mortem and try to understand what went wrong, what we need to do in order to fix that so it doesn't happen again. So the post-mortem surfaced two big major things. First of all, the safety mechanism didn't work. We had to go in and fix the system ourselves. Had the safety mechanism worked, it would be still a severe incident, but not as severe as it was. And second, which I think is more of a design type of thing, the safety mechanism only works after a crash. So the system by design needs to crash in order to improve its reliability, which I think is something that we had to improve. So let's talk about the safety mechanism and why didn't it work. Super simple explanation for that. Someone commented it out of the code. During one of many code refactorings that was going on by one of our top engineers, it was somehow left out, and it just didn't work. So how come we didn't notice that someone commented it out of the code? It's a critical piece of code. Why wasn't it picked up by our testing? And you guessed it, simple explanation. We weren't testing it. So that was a big shock to us. We were used to moving fast as a startup company, doing things very fast. However, this was that was not okay. And you could say that we had our priorities completely wrong because we had tests for tons of stuff. We had tests for what's going on when you try to log into the management console and you have a monkey jumping up and down on your keyboard, or what happens when you go to present on SREcon Europe and Docker says that you need to upgrade your OS. But we didn't have any tests for this super critical piece of code, which is a shame. And we realized that we need to find a way to communicate and to reason about the reliability of our system so we wouldn't be making that mistake ever again. So we came up with something that is pretty simple. We call it the Incapsula Reliability Framework, and it stuck. And we like it because it's simple. It allows us to communicate, talk about, and reason about the reliability of our system. And we also use it to make decisions, which is great, and it's super simple. It revolves around 3 levels of priority. We have P0, P1, and P2. And these represent levels of the Incapsula service, so to speak. So P0 means our customer traffic is up, websites are protected, they are available, and everything is fine on the runtime, so to speak. P1 represents all the stuff that we as an operator need to do in order to operate the service. Could be to push out configuration changes or code fixes if we must under fire. And P2, that's basically business as usual. Everything works, runtime works, operation works. Customers can log in, they do whatever they want, everyone's happy. And we use these priorities to obviously plan our work. So simple example, if we have a list of a few bugs, we will obviously work on the P0 bugs before we work on the P1 and P2. But more importantly, we use this as a guideline in order to architect new stuff and fix old stuff in the system. We divided all of our software components between these level of priorities, and we take that into consideration when we build stuff. So for example, proxy is P0, obviously, and management console is P2. We don't want to have a hard dependency between a P0 component and a P1 or a P2 component, for example, from the proxy to the management console. Great. So we use that ever since. We have it on our Jira dashboards. We categorize all our bugs, all our tasks, all our issues, all our technical debts according to these priorities, and it allows us to be conscious about what we spend time on and work on the most important things. So let's dive in on how we can fix the fact that the safety mechanism only works after a crash. And when we started thinking about that, our initial line of thought was, okay, we like to push changes fast, let's slow it down. Let's push it gradually. So let's push it maybe to 1 system and then to 2 systems, 4 systems, whatever. But when we thought about it a bit more, we couldn't tell how slow is slow enough. In addition, eventually, we will still get to a point where we have some systems with the configuration change that are live systems, and they might crash, and that would cause some impact for customer traffic. And we didn't want, at that point, to start degrading the agility that we provide to our customers, which they love so much. So when we did some more thinking about this topic, we realized that we were actually dealing with 2 types of problems. And we can solve each problem independently. So the first type of problem is what happens when we have an issue when we load the configuration change. So that's a well-defined time that we can that we can work on. And second is a crash when we evaluate the rules against an HTTP request. We don't control the timing of that. That could happen out of the blue. It could happen in one system. It could happen in two systems. We don't know when that will happen. But for the first item, we do have a singular point in time in each system where we can do something to make it safer. So, and for the second point, we had a safety mechanism in place. We uncommented it. We tested it. We added more tests to it. And we were kind of happy with the reliability that we provided there, because the chance of getting a very specific traffic pattern that causes an issue on the proxy on a very large number of our servers, which are spread worldwide, is very, very low. And we have the safety mechanism to recover from that gracefully and not get into a crash loop. And our service is resilient enough to withstand a few servers that are down. And we were happy with that. But I'll get into that in more detail also. So let's talk about what you can do, what we did when our system is going through a configuration change. So we kind of started in a sort of a deadlock, because we don't want to publish bad configuration because that might cause a crash, right? But a crash only happens when we publish. So how do we solve that cycle? So we don't want to crash, but we have to publish. And what we did was we just realized that we could publish to a whole different system on the side, because remember that we are now dealing with the problem of handling the configuration update. And that's orthogonal to the problem of how we process traffic against these rules. So when we zoomed in on the problem, we were able to find a solution. And we call the solution RevLite Sandbox. So here we have the same diagram as before, a bit dummied down. We have the management console, changes go into the leader repository, being replicated to the local repository and being read by the application. And we added to that a new subsystem that we call the sandbox. So in the middle between the management console and the leader repository, we have a sandbox repository, and changes first go into the sandbox repository. We added one more server to our service that we call the sandbox proxy. We also have a sandbox behemoth. We added a new server with a proxy application that is reading off a local repository that is synchronized from the sandbox and not from the leader repository. The repo server has an application running on it that monitors the proxy application on the sandbox proxy. And whenever it detects a problem with the proxy application, it can react and stop configurations from going into the leader repository. So, for example, I have a bad configuration change from the management console going into the sandbox repo. Now it's in the sandbox repo. It's now in the local repo. It's now being loaded by the proxy sandbox application. But now the repo server detects that the application is either not responding, maybe it crashed. It detects maybe that the application reports, hey, this configuration update did not pass validation, so I'm not going to load it, so I'm going to stick to the previous version. And the repo server knows that now we have a problem. Whenever that happens, we sever the connection between the sandbox and the leader, and we keep the bad configuration contained in the sandbox environment, and our production environment is safe from that change. Okay. So that was really cool. We were very proud of the sandbox mechanism, but there's a concept, I think I saw it in your Relic presentation some time ago, and it's called flying till mistakes high. Basically, it means that we need to put enough safety into our system that we can recover from a first mistake and not do more damage when we try to fix the first mistake. We interpret that as we were not happy enough with the reliability that we had, because what happens if the sandbox doesn't operate correctly? What happens if we have a bug there? What happens if the sandbox doesn't detect a bad change? Or, other bad stuff can happen. For example, the configuration could be completely valid, but when it would be loaded, it would be disastrous in the sense that maybe it will stop all traffic for a site, for example, things like that. So it's not only crashes that we're talking about. In addition, the local repo could also get corrupted somehow. It's just a file system, stuff can happen, and the application is very dependent on the local repo's health. So what we did was, wouldn't it be cool if we could, when the application thinks there's something wrong with the local repo, just to go back to a previous version of that repo that we know is healthy and good. So we did exactly that. We are creating file system snapshots of the local repo. We have a snapshot that represents 5 minutes ago. We have a snapshot that represents an hour ago, and a snapshot that represents 24 hours ago. And these are updated all the time. We have a service running on the systems that is doing that work. And if we have a problem in the local repo, and that's application specific, each application has its own logic about what it means that the repo is bad, and it has its own thresholds and decision making around that. But it can decide that it wants to fail over to a last known good repository, and it can do it easily, and it can also go back 1 hour ago, and it can also go back a day before. And remember why this is so powerful. It could be that 20 hours ago, a customer went into the management console, they did a change, the change was fine, it was published, everything's good. But now, a certain type of traffic comes into the service and causes a big issue, and things start to break down. So the configuration is good, but it has implications which are bad and we want to avoid. And this allows the application to understand that it's not in a healthy state, and it can go back, sort of run back to a last known good repository. So this is very, I think, unique and interesting. We're using BetterFS to implement these snapshots. If you know BetterFS, cool file system, it has support to do these kind of snapshots on copy on write, so it's very efficient. And yep, so this is cool. So I think I'm a bit early, so leave you more time for a question. So wrapping it up, configuration changes are bad, stop doing changes. Well, we can, our system is built around the ability for our customers to do these changes. So issues can happen when we load the change, and that's a specific point in time where we can control what's going on and we can do stuff about it. Or they can happen after the fact, out of the blue, when you can't really correlate that to a specific point in time. So if you have an issue during a configuration change, consider sandboxing the change. This is what we do. Quarantine it if necessary. And if you encounter an unhealthy state around configuration and it's out of the blue, what we do is we try using this safety mechanism to detect bad objects, like I showed you with the sites, and try to gracefully degrade only those. So we try to surgically degrade the service and not everything. But if for some reason there's a more broad issue where a large number of objects is bad, or there's a configuration repository issue, we just roll back to a different version of the repository and start from there. And with that, I'll open it up for questions.